Regarding what is certainly known or beyond doubt, we say that we know or understand it. Concerning all the rest, we may only conjecture or opine. These are the words that Jacob Bernoulli wrote in his book Ars Coniectandi around 300 years ago. And this is the place where the word stochastics is first to be found, if you look at the history of mathematics. And Bernoulli wrote, he defined ars coniectandi or stochastique as follows. To make conjectures about something is the same as to measure its probability. Therefore, the art of conjecturing, or stochastics, is defined as the art of measuring the probability of things as exactly as possible, to be able to always to choose what will be found the best, the more satisfactory, serene, and reasonable for our judgments and actions. And this alone supports all the wisdom of the philosopher and the prudence of the politician. This is a translation by Oskar Scheinin from Latin. And if you look at this definition of stochastics, it's very broad. It relates to all estimation of things or likelihoods and probabilities. So you can think yourself whether that should be classified into mathematics, statistics, or something else. Certainly there were no computers 300 years ago, but if they had been there, surely they would have been included in this book of Bernoulli. And he might have mentioned machine learning and data mining in this definition. The history of probability started with maybe seriously around the mid-1600s, when Fermat and Pascal were exchanging letters and figuring out what is the fair value of some gambling game. And Christian Huygens was the first to write a book about this type of thinkings, and they developed the intuitive notion of expectation and probability. But it was Bernoulli who gave the first real big mathematical theorem about the law of large numbers, which says that when you take the average of independent or something which looks independent or chaotic, when you take the average of many of such events, there will be one number and not something which varies with the number of experiments. And this history of law of large number is long and it's still going on. But what we now learn at the university usually is the version by Kolmogorov from 1933. The second big classical result is the classical bell curve, usually attributed to Gauss. But it was de Moivre apparently who first found this shape. And later on, many people have contributed into extending and generalizing this result. And there's one Finnish named Jarl Lindeberg there, who gave a very general condition for the convergence to a bell shape. And interestingly, Alan Turing, who is very well known for artificial intelligence and theory of computation, when he was undergrad at Cambridge, he thought of this problem and he didn't know about the earlier results, so he proved the central limit theorem as an undergraduate and then showed it to his professors. And only then he learned about Lindeberg's earlier work. And this result was nevertheless published as a dissertation for Turing's fellowship at the King's College in Cambridge. A third interesting result is related to law of small numbers from Poisson in mid-1800. And what does the law of small numbers tell us? It tells us that if you think of completely random events in time, and then you look at some time interval and you count them, and you ask, okay, how many there are? Poisson found out that if things are completely random, then this number should follow a certain one mathematical distribution, which is now known as the Poisson distribution. And to test Poisson's theorem, we can try with some data. So here is some statistics from Teemu Selänne's career in NHL. And the statistics tells us that he has been usually, on the average, he has scored 1 point per game. And if we take this one number, just one number, 1 point per game, as our parameter and feed it to a Poisson distribution, we get this type of prediction. For example, we predict that there should be 90 games in his career where Teemu scored 3 points. And when we look at the real data, this is what the real data tells us. And as you see, these numbers are not correct. So the prediction is wrong, but that's what it always is. It's never precise. That's the spirit of stochastics and statistics. But nevertheless, you can see that this prediction has certain value, definitely. And this is an example how the theorems and laws of stochastics, how they are connected to real life. Now let's do one experiment. When I count to 3, I ask you all to take a deep breath. So 1, 2, 3. Okay, and now I'm happy to see that this experiment went well, because I see none of you suffocated due to lack of oxygen in the air. What we know from physics is that oxygen molecules are impossible to predict their future location in a future time instant. So the oxygen is randomly moving in the air, and they are moving independently of each other molecules, and that means that there's a positive probability that all the oxygen molecules would be, let's say, placed in this corner of the room at a certain time instant, and we would all suffocate. But this didn't happen during the experiment. And the reason is that luckily the epsilon is so small number. It's super astronomically small. That's what we know, and it's not hard to check. What's more important is that although a single molecule is randomly moving in space, the full system, the ensemble of molecules, the distribution is not changing over time, so the air here is more or less in statistical equilibrium. And because statistical equilibrium is so vital for our well-being, it's important to try to know when some measured thing is in statistical equilibrium or when not. If you want the answer to the question, is there a climate change, for example, what we can do? We can go and try to get historical measurements for temperatures. And that's what scientists have been doing. This plot here is a measurement from Antarctica by drilling kilometers of ice and then reconstructing the temperature during the past 10,000 years. And if you look at the time series here, you can ask yourself, is this in statistical equilibrium or is it not? Certainly this is a very hard question, and there's no trivial, easy answer to this. How can stochastics help answering these type of questions? The theory of stochastic stability is devoted to this type of questions. It's mathematical theory of convergence towards equilibrium and the existence thereof. So, because most random systems are not bounded over time, they cannot converge to a single fixed point. So in this sense, they never are stable. But they may be stable in the sense that they keep returning to their earlier states, or they might approach a statistical equilibrium, as in the case of air molecules. And the mathematical problem we care about are to the existence theorem, is there a steady state? And if there is, how fast things would go to the stable place if we perturb things a little. For example, about the speed of convergence, you can ask how many times you need to shuffle a deck of cards for it to be completely random. You know that the more you shuffle, the more random the deck of cards gets, and the steady state will be the completely uniform distribution over all permutations of cards. The classical place to study stability is random walks, and the famous theorem of Georg Polya says that the symmetric random walk on the integer lattice is weakly stable, that is recurrent in 2 dimensions, and it's transient in 3 or more. In layman's terms, Shichuo Kakutani has provided a nice translation. He says that a drunk man will find his way home, but the drunk bird might get lost forever. Here, the drunk man represents a random walk in 2 dimensions. A drunk bird is flying in 3 dimensions. And theorem of Polya says that the man and the bird are completely different species mathematically. Another interesting and important result in this type of studies is done by Søren Asmussen, Peter Glynn, and Herman Thorisson more than 20 years ago. They studied that can you recognize when some random walk has reached the equilibrium or has forgotten his or her initial state. And the result is that this is possible for random walks on finite sets. There is a time when things get forgotten precisely, but this time is random. Later on, the same observations was independently found in computer science by Propp and Wilson, who found the idea and they applied this to create a very clever exact simulation algorithm for random processes. It's called the coupling from the past, and it's very famous nowadays. Switching to queuing networks, a network of queues is modeling like in a factory, for example, how things move, or in the internet, how files are moving. And the population in the network, the queue lengths, they actually are closely one-to-one correspondent with random walks on the n-dimensional space, or the positive part of it. And what does it mean that the queuing system is, the traffic moves steadily there, the road traffic moves steadily and it's not getting congested? It's actually one-to-one correspondence with a stochastic stability of the random walk. And maybe the deepest theorem here is from David Gomarnik, MIT, who gave the theorem that if the dimension is higher than 5, the general stability problem is algorithmically undecidable. This is a very negative result for us mathematicians. But luckily, when I was a postdoc in Eindhoven, Netherlands, I was not aware of this negative result. So we worked on this problem together with Sem Borst and Mathieu Jonker. And actually, we proved the positive answer to this question. But we had one extra assumption. It's about monotonicity. So if we assume that the service rate of one queue cannot increase due to arrivals to other queues, then we can write down an algorithm for deciding is there stability or not. As an application of stability studies, if you think of peer-to-peer communication where messages are replicated and one message can replicate with different users, that's actually what happens in Twitter and things like this nowadays. There the dynamics is a bit more complicated because there's nonlinear effects like exponential growth of communication locally. But there, if you want to analyze the capacity, how much information can flow through this type of systems, you can model it as this type of population dynamical model. And then the throughput capacity will be the maximum input rate for which the system, the population, is stochastically stable. Key result here is the recent paper by Chu and Hayek, where they gave a very complete, comprehensive picture about this type of dynamics. Let's move on to another topic. On the left of this picture is a satellite image of River Nile. And on the right, there's a stack of internet routers. And the question is, what is common with these two things? That's shown in the middle. In the middle, what you see are measurements from Bell Laboratories conducted by Walter Willinger in mid-90s. And the pictures show you the traffic measurements from the network over 3 different time scales. And what is a bit fascinating here is that the pictures look the same in all time scales. So there's something fractal-like going on there. And the same thing can be seen if you measure the River Nile water heights. And Harold Hurst was the one to study this River Nile water. And what is known from Nile? In the Old Testament, there's a phrase where Joseph was asked to predict what will happen in Egypt in the future. And what Joseph answered, he said that there will be 7 years of abundance and then 7 years of famine. And maybe this prediction was not out of nowhere, because if you look at this red curve here, that's actually the real measurements of River Nile during the 600-year period of time. And what you see in the picture is that there are lots of bursts, some periods of low levels, some really big bursts of high levels, and that's manifesting a stationary time series or stationary-looking time series, which is not fitting to any of the well-known ARMA models or things like this. And then people started to think, okay, what would be a mathematical nice model which would capture this type of burstiness in a single parameter, hopefully. And Mandelbrot was the person who made this, saw the importance of this. It was Kolmogorov earlier who had written in 1940 a mathematical paper on this process, but Mandelbrot sort of gave to big attention this definition of fractional Brownian motion. There you see the parameter h, and then you see dB, that stands for the Brownian motion. So with this formula, you can model something where there's a long-range dependence and strong burst occurring. But then we were sort of thinking the similar question in multiple dimensions, that can you go from one dimension to many dimensions? And together with Ingemar Kai, Ilkka Norros, who is here in the audience, and Volker Schmidt, we worked on this, and we found a physical explanation for the kind of appearance of this Hurst parameter by looking at superpositions of random materials with power law distribution. And with the same thinking, you can think also long-range dependence or strong correlations in random sets. And these type of correlations have been observed, for example, in the microstructure of paper here in Aalto University, Ala Nissilä, or in the distributions of galaxies and galaxy clusters. And if you want to try to construct a mathematical model here for such power law random materials, what Swedish Bertil Matern suggested is that just take randomly placed balls and then delete some of them. But then there's a question, will the long-range dependence still be there? The answer is yes in most cases. With the doctoral student Mikko Kuronen in Jyväskylä, we worked on this. Okay, finally, I'd like to say a couple of words about the mathematical methods in probability and stochastics. Usually, analysis and discrete math are what comes to mind. These are the building blocks for probability, but that's not all. There's something else. And what is this something else? I might call it pure stochastics. And that's coupling techniques and stochastic representation theory. Coupling refers to simulating mentally two random things using the same seed. This is a crime in computer science usually to do because you get biased samples. But if you are committing this crime in a clever way, that may give you a way to prove big results in, let's say, in the convergence of randomized algorithms, etc. Wolfgang Döblin was the pioneer until he tragically died at the age of 25. Two other famous stochastic representations are by the Ukrainian mathematician Skorohod and the German mathematician Strassen. But I might like to conclude here by saying something about the future trends of probability. So During the past 100 years, the main focus of probability has been focusing on random functions. During the past 50 years, the focus has been shifting more to spatial random structures, like multidimensional random walks or self-avoiding random walks and things like this. And right now, I think the future focus will be on random anything. So random graphs, random matrices, random measures, and so on. And what's special about random measures? First of all, you can think if you have some very rough functions which cannot be differentiated, for example, random measures can be a way to view them as random generalized functions. Or if you work with data, maybe it's big data or small data, but maybe it has a variable structure which is not well defined. For example, sometimes you don't have well-defined dimension for your data, or the dimension may change over time. When new data comes, it may be in different dimension. And then the traditional mathematical models may be in trouble, but with measure-valued things, you get automatically the flexibility of being dimension-free. And with this, I would like to conclude and thank you all for your attention.